All right, so as promised, we're starting Chapter 9. We're going to put in some splashes of Chapter 11 as well. So we're actually covering two chapters at once. So Chapter 9 is on solutions, and Chapter 11 is on acids and bases, which are solutions. They're just special types of solutions. And today is, I need my pen, April, come on, April 14th, goodness. All right. So there's a lot of concepts in this one. There's a little bit of math, but there's more concepts than anything else. So if the math is really hurting you, you're getting a break for chapters 9 and 11. You just got a little bit. So the image on the right, you see a patient getting their blood pressure taken. They're hooked up to dialysis. Your body, lots of fluids. Okay, so there's water, there's blood, and there's different things in the blood in your body called electrolytes. And the concentrations of those electrolytes and different waste products and stuff like that, those are all part of the solutions in your body. So we're going to learn more terminology about electrolytes. We're going to learn about some of the other things that are in your blood. First, we have to start with the very basics. Let's talk about what a solution is. So a solution is a homogeneous mixture. We talked about homogeneous versus heterogeneous. Homogeneous just means that if you mix them together, you can't look at it and see that there's more than one thing in there. So if you look at the example on the right, there's a person pouring salt into water. That's a solution. You're going to mix it up. You're not going to be able to see that was salt. But if you took a sip of it, which I wouldn't advise you, then you would know there's more than just water in there. Okay? The two things that are part of a solution are the solute and the solvent, and we'll talk about that in a second. And solutions have a larger amount of something called the solute, and the larger amount is the solvent, the smaller amount is the solute, and we'll talk about how you can identify those two. So the solute, we said that is the smaller part of the solution. I may end up having to type for this because Blackboard has been giving me issues. So that's the small part of your solution, the thing that you're adding to it. So if you're making a salt water solution, you're adding the salt to the water. The salt is the solute. It can be a liquid, a gas, or a solid, and it's going to be spread evenly throughout the solution. The solute and the solvent will eventually have the same physical state. So I'm going to keep going back to the salt water example because that's something that we can all relate to. You could also think about sugar and water. So if you're making Kool-Aid or lemonade or something like that, you're adding sugar to water. That sugar or that salt, that's a solid. And when you add it to the water, it eventually becomes aqueous. It's dissolved in the water, so they're the same physical state. You can't separate the solute from the solvent. So if you've got salt water, you can't separate it just by filtering it. You can't pour it through a filter and catch all the salt. You have to dry your solution. You have to evaporate it. And then you have the salt left and the water is evaporated off. Okay. Solutes are not visible. You can't look at the glass and see little particles of salt, but you can sometimes see a color change or something like that. So these are the characteristics of solutes. And the solute is the small part of the solution, what you're adding to the solvent. So this is a visualization of dissolving copper 2 sulfate, which forms a very pretty blue color when you put it in water. So The blue particles are the copper 2 sulfate, and then the other particles, the kind of grayish color, that's the water. So it's a nice visualization of what happens when you add a solute to a solvent. This table is just some different examples of things that you have likely encountered. I know that thinking about a solid solution is kind of weird, but if you think about brass or steel, those things are combinations of metals. And so it's a mixture, and you have a little bit of one metal and a lot of another. So with brass, it's a little bit of zinc in copper. And with steel, you're adding some carbon to iron. So that's just examples of solid solutions. But there's liquid solutions, gas solutions, all different kinds. Are we good so far? We just talked about solutes, the characteristics of solutes, and some different examples of what solutions are and what the solutes are in those solutions. Raise your hand if you're good. Thank you, Kristen. Lone soldier holding it down. So unfortunately, this chapter is going to be a lot of me talking about stuff, and then we'll do some examples. It's hard to be as interactive with this material, but I'll do my best. So we talked about the solute. That's the thing that you add to your solvent. Now we're going to talk about water as a solvent, because that's mainly the only solvent that we're going to be talking about. We're going to be talking about dissolving stuff in water. Water is a very common solvent. It's polar because when you think about water, you should be thinking this little cartoony here. So that's a water molecule. And this hydrogen-oxygen bond is polar. That means that there's a difference between the electronegativity of the oxygen and the hydrogen. Hydrogen bonds are really important, and so you'll see this throughout all different types of biological compounds. You'll see hydrogen bonding playing a really important role in either being, making something into a solution or just in general interacting with other compounds. So because water is a polar molecule, you have partial positive and partial negative charges. So there's a partial negative next to the oxygen, and there's partial positive next to both of the hydrogens. So that little kind of funky D with the plus or minus, that's a partial positive or partial negative. When you're making a solution, the solution has to overcome two different interactions. There's the solute-solute interaction. So if you think about your salt, that salt is a solid, which means that it's in a crystal lattice form. It's interacting with itself. And then you have solvent-solvent interaction. So the water molecules are interacting with themselves. And in order for a solution to form, the interactions between the solute and the solvent has to overcome the interactions between, let's say, the salt crystals and the water molecules. So you have to get them to commingle and overcome those other interactions. So some things will not do that. One example would be like oil and water. They don't mix. We'll talk more about why, but there's a lot of interaction between the water molecules themselves and the oil molecules themselves And those interactions are so much more favorable than the water mixing with the oil that you don't get a solution. And that leads us to the like dissolves like. If you've had any kind of chemistry class, you've probably heard this before. So solutions will form when the solute and solvent have similar properties. So water, we said, is polar. So that means that it can dissolve things that are polar, and it's not going to dissolve things that are nonpolar. So the oil and water example would be an example of trying to add something that is nonpolar to water. So nonpolar, don't even think about it with water, okay? Like dissolves like. Examples of ionic solutions or ionic solutes, things that will dissolve in water. We've been using the salt example a lot, but anything that's an ionic solute will dissolve in water. And the reaction that happens, if you have a solid, think about, pouring salt from a shaker into a cup of water. So you see the H2O with the L in parentheses. That means that you're adding it to water. Just like a recipe. Add water. Maybe not a great recipe, but it's a recipe nonetheless. When you add that salt to the water, you're going to get ions, separate ions. You're going to get a sodium ion and a chlorine ion. And those ions will become hydrated, which means that they're surrounded by water. So I like this depiction over here where you've got the sodium atom in the middle, and then there's hydrogen, and then there's waters all around. So the red is oxygen and the white is hydrogen. So those little molecules are waters. That's what happens when you dissolve an ionic solute in a solution. Are we good so far? We talked about ionic solutes just now, like dissolve like, and the fact that water is polar, and it is a very common and universal solvent. Okay. So if we're good so far, you can raise your hand. Thank you. Let's talk about polar solutes. We talked about ionic ones. Now we're going to talk about polar solutes. So if you're polar, you need something like you to dissolve you. So that means you're going to need a polar solvent. An example of a polar molecule is methanol. That's a type of alcohol. I usually write it like this, CH3OH. It's this OH group, that's the alcohol. Okay. Alcohol is polar. It's got hydrogen bond in there, but there's also some carbon-hydrogen bonds which are not so polar, okay? So that means there's some partial charge on one end and not on the other. Methanol will dissolve in water, but you're not going to get ions like you do with an ionic substance. So you're just going to get the methanol, which is here, interacting with the water, which here's one water molecule here, there's another water molecule. So you just get methanol surrounded by water, versus the ionic solutes where you had ions being formed, like the sodium ion and the chlorine ion. Okay? So remember those two differences between the polar solutes and the ionic solutes. Now we're going to talk about nonpolar solutes. So I talked about oil, grease, those kinds of things don't dissolve in water. Do not dissolve in H2O. Water is polar. Nonpolar molecules don't like that. They don't want anything to do with charge. So a nonpolar solute requires a nonpolar solvent. So remember those three differences between ionic, polar, and nonpolar solutes. Know which ones will dissolve in water and which ones won't. So a quick learning check. Here we need to identify the solute in each of the following solutions. And remember, the solute is the small part added to whatever your solvent is. So for A, 2 grams of sugar and 100 milliliters of water. Which one is the solute? The sugar or water? You can write it in the chat. The solute is the small part that you're adding to the solvent. So it's the sugar. You're adding the small part to the large part. 2 grams of sugar is pretty small. 100 milliliters of water, much bigger. Let's try B. We've got 60 milliliters of, it's no worries, D. 60 milliliters of ethyl alcohol and 30 milliliters of methyl alcohol. Which one is the solute, the small part? Yeah, the methyl alcohol. All right. So you guys get that. I'm not going to stay on this one for too long. The smaller one of the two is going to be the solute. So don't forget that. Okay. And there's the answers there for you. All right. Now let's have a question about how dissolving in water works. So when you have a solid, lithium chloride, it's right here, is added to water, it dissolves. Why? So A says the lithium ions are they attracted to the partial negative of the water or the partial positive of the water? So let's talk about this a little bit. Right here we see Li+. That tells us, it clues us in, that we're dealing with an ionic solute. So we're going to get ions when we dissolve this in water. Opposites attract. So the positive lithium ion is going to be attracted to negative or positive charge. You can write that in the chat. Negative or positive charge. Right. It's going to be attracted to the negative charge. So that means for A, the lithium ions are attracted to the oxygen atom of the water. So now B, the chlorine ions are attracted to, is it 1, the oxygen atom, or 2, the hydrogen atom? Hydrogen. Right. So that's how things dissolve. They're attracted to the partial positive or the partial negative when it comes to an ionic solute dissolving in water. Okay, great. And there's the answers. One last question. Which of these solutes will dissolve in water? There may be more than one answer, so you can put whichever letters are associated with it, which ones will dissolve in water. So we're definitely getting A, but D, you got it. It's A and D. So HCl, that is an acid, okay? And acids do dissolve in water. The other two are nonpolar. So keep in mind the polar, nonpolar, and how things dissolve in water, because now we're going to talk about electrolytes and non-electrolytes. So we're talking about the ions that are formed in water when you're dissolving something and how that can affect your body and the different roles that they play. You may have heard my toddler just have a little giggling fit. Okay, so electrolytes. We're talking about things that when they dissolve, they can hold an electric charge. So if you dissolve salt in water, you can actually light up a light bulb, okay? It's not a lie, you can. Strong electrolytes will completely dissociate. So you're going to have your ions form. So think about strong acids, like the HCl from the last question that we had, and ionic compounds. So always think about salt, okay? Those are examples of strong acids and ionic compounds. This little equation here tells you how something dissolves. We went over that before, but you're going to need to remember this form for how something dissolves. So when a strong electrolyte dissolves, you need to be able to write the different ions that come from the solvation, okay? So in this case, you're going to make sodium ions and chlorine ions. That's a strong electrolyte. Now, I mentioned strong acids. We talked a little bit about acids in terms of being polar or being ionic. So let's talk about acids a little bit more. This is from chapter 11. So the acids that we're talking about are called Arrhenius acids. You don't really need to know that. Just think about acids. An acid is something that produces hydrogen ions when it dissolves in water. So our example of hydrochloric acid, HCl, when it's dissolved, it makes H plus and Cl minus. It's an electrolyte, and it's actually a strong electrolyte because it's fully dissociated. Okay. That's for strong acids. There are weak acids too, and weak acids do not fully dissociate. Weak acids are weak electrolytes. They only dissolve slightly in water. So you'll form a few ions, but most of the acid is going to be in the undissociated form. So if you have hydrofluoric acid, you'll get a tiny, tiny little bit of hydrogen, a tiny, tiny little bit of the fluoride ion, but most of the molecules will be intact hydrofluoric acid. We're going to detour from talking about weak electrolytes to talking more about weak acids, because that's mainly the only thing that we're going to talk about for weak electrolytes, weak acids and weak bases. Then we're going to come back around and do a recap for the strong and weak electrolytes and move on for electrolytes. So we're shifting from chapter 9 to some chapter 11 stuff right now. To keep going with the weak acids, we need to talk about its dissociation a little bit more. When you have your weak acid and you add it to water, you're going to form, sometimes you'll see it as just the H+, but what's really formed is the hydronium ion, which is H3O+, okay? You're adding a hydrogen to water. And then you're also going to get some kind of ion. So here we're showing formic acid being added to water, and you're making hydronium, and you're making formate. These two arrows here that go back and forth, that implies that there's some kind of equilibrium. I'm not even going to try to write that word. I'm going to type it. Okay. So whenever you see those two arrows, automatically think weak acid or weak base. It's a weak electrolyte. Okay. So far we didn't really introduce anything new from the other slides. Let's take that same formula that we had, the chemical formula, about formic acid dissolving in water. We can write a dissociation expression. And all that does is it talks about the different concentrations of the products and the reactants. And the balance of these two gives you what's called an acid dissociation constant, which is the Ka. The Ka tells you how strong an acid is. And we'll go over that in just a second. The form of the Ka, on top here, these are the products. So whatever ions you're going to form. So when you're writing your dissociation expression, you're going to put the products on top. And you're going to use brackets around it. So the hydronium ion is in brackets, and the formate ion is in brackets. On the bottom, you're only going to have your acid. Water is a pure liquid, so its concentration is constant. So we don't care about the water in our dissociation expression. So oh no, I just did that. I just erased it, y'all. Let's try that again. We said our products are on the top. Those are the ions. We said that we don't care about the water. And I'll use a different color for the reactant. In this case, it's just your acid. So that's always going to be how you write these. You put Ka is equal to, and on the top, you write your products. On the bottom, you write your reactants, which is usually just one thing. It's an acid or a base. In this case, since it's a Ka, it's going to be an acid dissociation constant. So let's go to the whiteboard. I'm going to give you a quick example, and I want you to figure out how to write the dissociation expression. I know it's not exactly fancy, but we have acetic acid. I'll try to draw in our equilibrium areas. So acetic acid, we'll put the water over here just for warm fuzzies, but we know it's there. That acetic acid will break down to hydronium and the acetate ion. When we write our Ka, what goes in the top? We said that the products are going to go at the top. So what are the products if we're dissociating this acid? Yeah. So we're going to have, right, H3O plus in brackets, and we're going to have C2H3O2 minus in a bracket. So that's the top part. What goes in the bottom? There's only a couple of choices left. I know it might be a little bit much to type. But what goes into the bottom? Yeah, it's that long thing. It's the acid. HC2H3O2. And that, again, is in brackets. So you'll probably need to be able to pick that out of a multiple choice or should be able to write it for your homework, how to write a dissociation expression. Okay. All right. Now we're going to go back to the slide. Still navigating. There we go. It was a long slideshow. All right. Come on. Oh, there's more than that. Okay. So we covered how to write the dissociation expression. Now we got to talk about the Ka, or the acid dissociation constant. So you can have actual concentrations of the different ions in your acid, and you can calculate an acid dissociation constant. When the value of the Ka is small, that means that the equilibrium is going to favor the reactant. So think about weak acids. A small Ka means weak acid. If the Ka is large, then that means you're going to favor the products. So you're going to fully dissociate like a strong acid. So a large Ka value, think HCl. So however you want to remember that, you can. But you'll definitely need to know small Ka, weak acid, large Ka, strong acid. We can also talk about bases in the same way. So a base is something that creates hydroxide. So instead of hydronium, you're making hydroxide. And the same rules apply for the base dissociation constant. If it's small, then it's going to be weak, a weak base. If it's large, then it's going to be a strong base. And a strong base that a lot of people are familiar with is sodium hydroxide. So if you can associate sodium hydroxide with a large Kb, which is the base dissociation constant, then you'll be able to remember the other. And when you're writing an expression, it's the same exact way that you would write for the Ka or the acid dissociation expression. You can write a base dissociation expression using the same exact rules. Your products are on the top, and your base is on the bottom. So same thing, just slightly different name. Raise your hand if you're okay with that, talking about Ka values, Kb, small means weak, large means strong. That's the summary. Literally like a 10-word summary of what we did. Good. Thank you. Okay. So this table is just just examples of different weak acids and bases and their Ka and Kb values. When you're doing your homework, if it's not specifically labeled as a weak acid or a weak base, this table can help you. So have it handy just in case you need to identify something as a weak acid or a weak base so that you can tell whether or not it's a strong electrolyte or a weak electrolyte. Okay. This table summarizes the characteristics of acids and bases in terms of the equilibrium position, whether the Ka is large or small, and all of that we just talked about. So this is a really good summary table for, again, when you're doing your homework or you're doing class participation assignments. So just keep that in your back pocket. If you want to copy it down in your notes at another time, you can do that. But it's definitely a good one to hold on to. We already did an example of writing an acid dissociation expression, but I will allow you to do this on your own time if you would like. And then if you run into issues, then you can email me or stop by office hours. So this learning check is here for you. All right. So let's recap, because we took a bit of a detour. Before we started talking about weak acids and bases, we were talking about strong and weak electrolytes. We're talking a lot about strength today. So strong electrolytes completely dissociate. So think about table salt and other ionic compounds. We can add to that list strong acids. And the way that reaction looks is you're taking some kind of solute, and we're calling it some kind of solid something. You're adding water, and you're forming ions, positive and negative ions. So that's the strong electrolyte. The weak electrolyte, you only get a little bit of ions. So remember, a weak electrolyte is going to have this reversible arrow. That means there's some kind of equilibrium going on, and you have mostly your undissociated molecule. So weak acids, weak bases, which we just talked about, those are weak electrolytes. There's still one more category of electrolytes to cover. Those are non-electrolytes. So these are things that dissolve in water, but they just dissolve as molecules. They don't produce any ions, and they don't conduct electricity. So if we took our methanol example, We were talking about methanol being a polar molecule because it has hydrogen bonding, the OH. It's polar, it dissolves in water, but it is not an electrolyte. Notice there's no ions over here. You just have the liquid methanol going to aqueous methanol, which means it's dissolved in water. So you've got water molecules all around each individual methanol molecule. So that's a non-electrolyte. This table, it summarizes strong, weak, and non-electrolytes. It doesn't summarize the reactions or what the chemical equations look like. So you'll definitely want to add that to this table so that you can remember that. So you can literally, if you're copying this into your notes later on, you can add another column for a sample chemical equation and put one for strong, weak, and non-electrolytes. So we good so far? Strong, weak, and non-electrolytes. I think I have some questions coming up. Yeah. So I'll do this first one. It says complete each for strong electrolytes in water. A strong electrolyte, is that going to fully dissociate, partially dissociate, or not dissociate at all? So how does a strong electrolyte work in water? You can put full, part, or doesn't for a strong electrolyte in water. We're talking about how it dissolves. Full, part, doesn't. Right. This will fully dissociate in water. So that means we're going to be making some ions. There are two ions here. We have calcium, which if you look at your periodic table, you would know it is one of the group 2A elements. So that means it's got a charge of 2 plus. And we have chlorine ions, which are negatively charged. There's 1 minus for the chlorine ions. And there are 2 of them. We get that 2 from this subscript here. So when you dissolve this ionic compound, you're going to break up the calcium from the chloride ions, and you're going to have 2 chloride ions and 1 calcium ion. So that means that it's C that represents this strong electrolyte dissolving in water. I want you to take a second and do number 2. And then in the chat, you can put what your answer is, A, B, or C. So this is a strong electrolyte. Both of them are strong electrolytes. So you're going to need some ions. So it's not B. We can rule that out. And it's between A and C. So vote for A or vote for C. I see you, D. You're saying A. That is our answer. It's A. And I take it that since many people didn't answer, that somebody's lost. So let's talk about it a little bit more. Strong electrolyte, we said that that's going to fully dissociate in water. That means that we're going to make some ions. I'm going to start typing here. We'll talk about that in just a second. So PO4, this is actually a polyatomic ion. So it has a -3 charge. That's why there are 3 potassium ions, or that's why there's 3 potassiums along with it, because potassium is positively charged. So this is reaching back to chapter 6 when we were doing naming of ionic compounds and figuring out the charges on different ions. So if you need a refresher on that, go back to chapter 6. That's where this is from. But even if you didn't know that PO4 was a polyatomic ion, you should have guessed either A or C, because A and C both have ions in them, and a strong electrolyte fully dissolves in water. Right. That was good practice. Which one of these represents the dissociation of a strong electrolyte in water? So now we're trying to figure out which one is a strong electrolyte. A, B, C, or D? Yeah. So this one is the strong electrolyte. And the reason is we're making ions. Which one of these represents a non-electrolyte? Definitely D. It's actually A, B, and D. So all of them are non-electrolyte, because you're not forming any kinds of ions, and you're not even partially dissociating. But yes, it's good that you can at least recognize one of them. So that's a little practice on recognizing electrolytes and classifying them. You'll need to be able to also write examples. So in this next one, write the write the equation for the formation of a solution for each of the following. So we've done a lot of the strong electrolytes. So what I want to focus on is B and C. So we'll start with B, writing an equation for the formation of a solution with the weak electrolyte phosphoric acid in water. This is going to be a long one to type, so I will give you a minute, and then I'll let you get the answer in your brain, maybe write it in your notebook, and then I'll write out the answer. So what you should get, is something where you're adding the weak electrolyte phosphoric acid. Since it's weak, we know that there has to be some kind of equilibrium. Let me draw my other arrow in. So you're going to add that acid to water, and you're going to form hydronium, which is the H3O+, and then you're going to form what's called the conjugate base, which we didn't cover that terminology, but you're going to form something that has a negative charge. When you take away one hydrogen from the phosphoric acid, then you have H2PO4, and it has a charge of 2-. So that was a little bit of a tougher one, but only because it had H3. The concept is the same. Questions on that? Thank you, Jayla. When them questions just hang out there in the ether, those seconds feel like eons. All right. For C, dissolving sugar in water, we're going to take that C12H22O11 solid. We're going to add our water, which I'm just going to say plus H2O over here because I can't really do the water over the arrow. And we're going to take that, and instead of it being a solid, it's now going to be a liquid. So that's the L in parentheses. So solid sugar, your key, solid sugar, that's a non-electrolyte. Just going to write non there. This big old molecule, that's absolutely not going to dissolve in water. Well, it will dissolve in water, but it won't make any ions or anything like that. It's not an electrolyte. Okay? So remember the different kinds of equations you can write for strong, weak, and non-electrolytes. We good to move on? Okay. So I think this is probably going to be the last thing that we get to for today. And this will round out 9.2, section 9.2. We talked about strong, weak, and non-electrolytes. Now we're going to talk about how we quantify those electrolytes. We use what's called an equivalent. So if you have watched any kind of, Grey's Anatomy, House, or any of those kind of medical dramas, you might have heard equivalent or EQs of something. We're talking about how much electrolyte or ion that provides 1 mole of electrical charge. When you're putting up an IV bag or something like that in a hospital, or if you're having an outpatient procedure, those IV bags have electrolytes. And there's always a balance of positive and negative ions. So you're going to have the same amount of positive as you do negative. If you have 25 equivalents, well, they use milliequivalents when we're talking about those little IV bags. So if you have 25 milliequivalents of Na+, you're also going to have 25 milliequivalents of chlorine or some other kind of balancing ion, but typically it's going to be chlorine, okay? So that's what it means when it says positive ions are always balanced by the charge of the negative ions. You're always going to have the same amount. When we're talking about IV fluids or intravenous fluids, that's IV if you didn't know, we're using milliequivalents per liter. And if you remember way from, I think it's chapter 2 maybe, when we talked about conversion factors and equalities, and we looked at all the different prefixes. So the M here is milli. So 1 equivalent is equal to 1,000 milliequivalents. You're going to need to remember that. This table and this slide summarizes what I was talking about with the total positive and total negative charge. And it also talks about the number of equivalents in 1 mole. So the number of equivalents is just going to be the number that you're going to take your ionic charge and then put EQ behind it. So magnesium has a charge of +2, right? So that's its ionic charge. The number of equivalents it has is 2 equivalents for every 1 mole of magnesium. You look at the ionic charge, that's going to tell you the number of equivalents. So let's do a sample problem. We have a laboratory test for a patient, and that test indicates a blood calcium level of 8.8 milliequivalents per liter. The first part of this question is how many moles of calcium ion are in 0.50 liters of blood. So we have to whip out our conversion hat, and I think it's going to be better if I type it. So there are really 3 parts to this problem, okay? So if we rewrite the question, what we have is 8.8 milliequivalents per liter is equal to how many moles of calcium. We can't just do that straight up. We actually need to break this up into parts. The first part, we're going to have to take the number of liters and convert that to the number of milliequivalents of calcium. The second part of this problem, we're going to have to take the milliequivalents of calcium. Let me start off by writing number 2. Convert the milliequivalent of calcium to equivalents of calcium, because we can't go directly from milliequivalents to mole. We have to get rid of the milli part. The third thing we have to do is convert equivalents of calcium to moles of calcium. And this is where we have to know the charge of a calcium ion. So the calcium ion is in group 2A, so it's going to have a 2+ charge. So I'm going to write that up here. Ca 2+. You'll need to remember that, and that's again from chapter 6, being able to look at the periodic table and figure out for the representative elements, the ones that have the A after their group or family number, and figure out what their charge is. So the first part, for going from liters to milliequivalents, we need to use the conversion factor that's given in the problem. So we're going to take our 0.5 liters and we're going to multiply by 8.8 It's a sad looking 8, y'all. Milliequivalent over 1 liter. What this does is it gets rid of the liters. So when you do that, you get rid of liters, you're left with milliequivalents. So that's the first part. Now we need to add on a little bit more. We need to go from these milliequivalents of calcium to equivalents of calcium. And we said 1 equivalent is equal to 1,000 milliequivalents. That's the equality, but we need a conversion factor. If we're trying to get rid of milliequivalents, should I put milliequivalents in the top or the bottom of this conversion factor? You can just write top or bottom. We're trying to cancel out the milliequivalents. Bottom. So milliequivalent should go on the bottom. That way it will cancel out. So don't forget to write the 1,000 along with it. That number travels along with the milliequivalent. On top, we're going to put 1 equivalent. That's the unit that we actually want to get to next. So for our second step, we're going to take those milliequivalents and divide by 1,000 to get equivalent. So that's equivalent of calcium. I'll put that in here. That's the second part. The third part, we have to take the equivalence of calcium and we need to make that into moles of calcium. We need to somehow get rid of equivalence, which means that we have to put that in the bottom. Can barely squeeze it in there. We said that 1 equivalent means that you have one, your ionic charge is 1. Calcium's ionic charge is 2+. So that means that you have 2 equivalents of calcium for every 1 mole of calcium. I'll type that out here. Ionic charge equals number of equivalents. So in this case, our charge is 2+, so 2 equivalents in 1 mole. So that's setting up the problem. Now we just have to do the multiplication. So when you put this into your calculator, you're going to multiply 0.5 times 8.8, divide that number by 1,000, and divide that number by 2. Put that into your calculator, see what you get. Yes, it's a small number, 0.0022. I should type this. You should get 0.0022 moles of calcium. So that's about as mathy as we're going to get for this part. You will have one of these for as part of your class participation, and then you'll have a couple of other questions that test your understanding of the different types of electrolytes, polar versus nonpolar, and how things dissolve in water. So that's where we're going to stop it for today. If you have any questions about anything, you can always email me and let me know. Things that I said in the beginning of class. One, since everyone has now finally taken the exam, you'll have your exam grades by the end of the week. And we're going to cover Chapter 9 and Chapter 11 together because they're related. Depending on how much time we have, we'll also cover, the unit is moles of calcium. So if we continue on to cancel out the equivalent, you're left with moles of calcium as your final unit. And I typed it out down here. Okay. So we're covering chapters 9 and 11 together. We're definitely going to get through that, and then we'll see how much of chapter 10 we get through. But I'm not going to bombard you with it. I'm not going to try to force feed an entire chapter in a day. That would be pretty cruel. Your exam 4 is going to be the last day of class, which is April 30th. And then your final exam is going to be May 6th from 3:30 to 5:30, which is a Wednesday. I'm going to make it so that all of your mastering chemistry homework is due by the end of May 6th. So you'll have a little bit more breathing room and time to try to work in finishing that mastering chemistry homework for chapters 9 and 11. If you have any other questions, you can hang around, put it in the chat, or if not, you're free to go.